Welcome to first lecture on renal physiology, physiology of excretion, mechanisms of urine excretion. All the lecture materials you can find in the Facebook group under Files category. And if you will have any questions, feel free to ask in the same group. These are the questions which we are going to discuss today. We will talk about functions of excretory organs, kidneys, skin, lungs, and the GI tract. We will also discuss the structure of the nephron, that is the structural and functional unit of the kidney, and we will talk about blood supply of the kidney. We will also talk about mechanisms of urine formation, glomerular filtration, and composition of the primary urine. We will discuss tubular reabsorption, a countercurrent mechanism, and tubular secretion. Then we will talk about final composition of the urine and methods of kidney examination, and clearance as one of it. If you can hear me nicely and I don't have to increase the voice volume, please let me know into the chat if the volume of my sound is okay or I should talk a little bit louder. So those people who has written their attendance, please let me know if the volume is enough or should it be any louder. So here on this slide, you can see the organs which belong to the excretory systems. So the first one is the skin which excretes water, sodium chloride, urea, respiratory system, and lungs, which excrete CO2 and water vapors. Digestive system, which excretes solids, undigested foods, wastes, water, salts, and liver as a part of the digestive system that is responsible for the excretion of various toxic substances, bilirubin, waste products, and drugs. And last but not least, urinary system and kidneys. Urea is excreted by the kidney, excess of water and salts. So kidney, they ensure that excess of substances, toxins, and waste products are excreted in urine. So now we will talk briefly about various functions of kidney. One of the functions is regulation of water and electrolyte balance. The second function is the excretion of metabolic wastes. And here we have urea from protein metabolism, uric acid from nucleic acids, creatinine from muscle creatinine, then products of hemoglobin breakdown and metabolites. Excretion of biologically active substances, hormones, and other foreign substances, specifically the drugs. Why is it necessary to talk about this function? Because you need to know how fast the drugs are excreted so that you can prescribe a dose that achieves the appropriate body levels based on the amount that is excreted by the kidney. Then we also have regulation of arterial blood pressure. It depends on kidney maintenance of sodium and water balance that provides regulation of the blood volume. Next function is the regulation of red blood cell production. For that you have erythropoietin that is produced by kidney, and the production of it is stimulated by the decreased partial pressure. So in case of renal diseases, they might result in diminished erythropoietin secretion, and as a result decreased in bone marrow activity as one of the important factors that might cause the anemia in case of chronic renal diseases. Next one is regulation of acid-base balance and also regulation of vitamin D production. Active form of vitamin D is made in the kidneys, and gluconeogenesis. So these are some, but definitely not all functions of the kidney. Let's briefly revise the anatomy of kidney. So it's the paired kidneys are bean-shaped retroperitoneal organs, and the cut surface, which you can see on the slide, of the kidneys has a pale outer region that is known as the cortex, and a darker inner region, that's the medulla. The medulla is divided into conical areas called renal pyramids, and the apex of each pyramid tapers towards the renal pelvis, forming the renal papillae. And the renal pelvis has a funnel-shaped upper end, and it's continuous with the ureter below it, which conveys the urine into the urinary bladder. So urine from each kidney drains into ureter and is transported to the bladder for storage and elimination via the urethra. More details will be given during the next lecture. This is where we will discuss the mechanisms of urination. So actually, the kidneys, they have the highest blood flow out of all organs. The blood flow in the kidney, it is even higher than the brain, liver, or the heart. So let's briefly talk about blood supply of kidney. Although the kidney constitutes less than 0.5 of a total body mass, in anatomy you might have seen how small they are, they receive up to 25% of the resting cardiac output via the right and left renal arteries. In adults, renal blood flow, the blood flow through both kidneys, is about 1200 milliliters per minute, which makes it about 400 ml per minute per 100 grams of tissue. But there is such thing as maldistribution of renal blood flow. Most of the blood goes to the renal cortex, less blood goes to the renal medulla and renal papilla. And in the kidney you can find primary and secondary capillary networks. So the glomerulocapillary network, the primary one, is between afferent glomerular arteriole and efferent glomerular arteriole. Here you will have high blood pressure in favor of glomerular filtration. And the secondary capillary network, which is the peritubular capillary network, it's made by branches of efferent glomerular arteriole. Here you have low blood pressure that favors tubular reabsorption. So a small summary to recap. The kidneys normally receive up to 25% of the cardiac output, which is a very high rate of renal blood flow is needed to supply enough plasma for the glomerular filtration to occur. And all of the blood entering the kidney passes through larger branches of the renal artery to reach the glomerular capillaries in the renal cortex. And renal perfusion is achieved with the typical system of arterial perfusion pressure that is about 90 millimeters of mercury. And high rates of renal blood flow are possible because of the renal vascular resistance and because the resistance is low. And the pressure decreases measured across the afferent and efferent arteriole, and it demonstrates that vascular resistance is shared between arterioles. Blood is completely filtered at the renal glomeruli. That means the whole amount of blood which flows to the kidneys has to pass through the glomerular capillaries before entering the venous system. And renal arteries arise directly from the aorta. High pressure in the aorta facilitates the high blood flow to the kidneys. And renal glomerular capillaries from high pressure bed with a pressure of 60 to 70 millimeters of mercury, much greater than the capillary pressure elsewhere in the body. And this high pressure is maintained in the glomerular capillaries because the diameter of afferent arteriole is more than that of efferent arteriole. And the high capillary pressure augments glomerular filtration. Peritubular capillaries, they form a low pressure bed with a pressure of 8 to 10 millimeters of mercury, and this low pressure helps tubular reabsorption. Autoregulation of the renal blood flow is also nicely developed in the kidneys. And blood flow to kidneys is measured by using plasma clearance of para-aminohippuric acid. So at this slide you can see the overview on the blood supply of the kidney, which begins with the renal artery and ends up with the renal vein. And here you can see the primary capillary network, which is made above afferent arteriole which then empties into the glomerular capillaries and then into the efferent arterioles. After that, you will have secondary capillary network, which is the peritubular capillaries and or vasa recta. So here you can see the reason why blood flow in the kidney is maldistributed, and why most of the blood goes to the cortex. It happens because all of the glomeruli, they are located within the cortex, and that's the reason why cortex we need to provide the highest plasma flow to the renal cortex. Renal medulla has very much less of the blood supply, and renal papilla very less of blood supply. So let's take a closer look at the secondary capillary network. One of the examples is peritubular capillaries. Peritubular capillary bed receives water and solutes reabsorbed from the nephron, and it's being supplied from efferent arterioles, and it is in series with the glomerular capillaries. Filtration of protein-free fluid from the glomerular capillaries increases the osmolarity of blood entering the peritubular capillaries, which assists in water reabsorption from the nephron. This promotes glomerular-tubular balance, in which the rate of proximal tubular absorption is proportional to the rate of filtration, providing consistent rate of fluid delivery to the distal nephron. Another example of a secondary capillary network is the vasa recta. Vasa recta are long capillary loops, as you can see in the slide, branching from peritubular capillaries which travel with the loop of Henle. Less than 10% of renal blood flow through the vasa recta to the renal medulla, and only about 1% reaches the renal papilla. And low blood flow in the renal medulla helps to preserve the medullary hypertonicity necessary for the concentration of urine, but it causes to be very susceptible to ischemia in the settings of hypotension or renal vasoconstriction. So the next question which we are going to discuss, it will be about structure of the nephron. As you know, the functional unit of the kidney is a nephron, a tube that consists of different transporting epithelia in sequence, and each kidney has around 1 million nephrons. That is composed of the corpuscle, renal corpuscle, the system of renal tubules, and it ends up with collecting ducts and papillary ducts. So here you can see more details on structure of the nephron, and it composed of two major components, the glomerulus and the renal tubular system. And as you can see here, you can find few histologically distant segments. The glomerulus is the site of primary urine formation, where blood plasma is filtered into the nephron. And the glomerular capillaries are enveloped by the blind-ended upper part of the nephron, which is known as Bowman's capsule. That's the space. Filtrate flows from Bowman's space into the proximal tubule, which consists of convoluted portion and straight portion. And the proximal tubule is continuous with the loop of Henle, which is a U shape. So here you can see the tubular system in details. This is the PCT, and this is the loop of Henle. And a loop of Henle descends into the medulla before turning back towards the cortex. In loop of Henle, you can find three functional parts. They are the thin descending limb, then you will have the thin ascending limb, and you will have a thick ascending limb. Also, you can find macula densa. It's a short segment that passes close to the glomerulus and connects the thick ascending limb to the distal tubule of the cortex. And distal tubules from approximately 6 nephrons converge via the single collecting duct. So as you can see here, the convergence happened. Now, more details on structure of the renal corpuscle. Here you have Bowman's capsule, which surrounds the capsular space, and you have podocytes that cover the capillaries to form the visceral layer. And also you have simple squamous cells from parietal layer of the capsule. And glomerular capillaries, they arise from the afferent arteriole. As you can see, its diameter is wider, as we've mentioned. And it will form a capillary meshwork of the glomerulus before emptying into the efferent arteriole. And one more specific feature of the renal corpuscle, that the vascular system in the glomerulus, it is purely arterial. So here you can see the structure of the filtration barrier in the renal corpuscle, which consists of 3 layers. You have a capillary endothelium of the glomerular capillaries, then you will have a rather thick basement membrane and a single layer of podocytes or epithelial cells. So this is the structure of the filtration barrier. And to make it a little bit easier for you to memorize the structure, you can look at it in the following way. The first layer of endothelial cells of the capillaries, this is the fenestrated type of the capillaries, and fenestra, they are known as windows. So you can look at it as a slice of a Swiss cheese with these kind of holes in it. The second layer, the middle layer, is the capillary basement membrane, but it is not a membrane in the sense of a lipid bilayer membrane, which you studied in the very beginning of physio course. But you would rather look at it as a gel-like cellular meshwork of glycoproteins and proteoglycans. And the structure of it, it looks like a kitchen sponge. And the third layer consists of epithelial cells called podocytes that have an unusual octopus-like structure because of the projections of the podocytes. So once again, the first layer, which is slice of a cheese, the middle layer, which is the kitchen sponge, and third layer, which is the octopus-like structure. And here on the microphotograph, you can see how exactly this octopus-like structure of the podocytes it looks like. And this is the filtration barrier at the slide. Now, all of the nephrons could be divided into 2 distinct types. The 2 types of nephrons are about 85% are the cortical nephrons and around 15% are the juxtamedullary ones. Glomeruli of the cortical nephrons are located at the outer cortex and the loop of Henle is really very short. Juxtamedullary nephrons, they have glomeruli located deep into the cortex, and they have very long loop of Henle, many extendings of the tip of to the tip of the renal papilla. And juxtamedullary nephrons, they are salt conserving nephrons, and they are important for urine concentration. When effective circulation of the blood volume is reduced, a higher proportion of the renal blood flow is directed to the juxtamedullary nephrons, thus helping to conserve extracellular fluid volume. So here you can have a closer look at the cortical nephron, how it looks like. As I told you, these are the most numerous nephrons that we have in kidney, and renal corpuscle is in outer cortex, and the loop of Henle is very short. It does not descend deep into the medulla. And here on the slide, you can see the structure of the juxtamedullary nephron. And in this case, renal corpuscle, it lies close to the medulla. and there is a long loop of Henle extending into the deepest medulla, enabling excretion of diluted or concentrated urine. And there will be a small difference in the structure of the loop of Henle. Here you can see that we have descending limb of the loop of Henle, thin ascending limb, and thick ascending limb. These specific features of the structure of the loop of Henle will provide a specific function of it. Now, on this slide, you can have a summary of two types of nephrons. So what do we have? Cortical nephrons, they are more in number. Then the situation of the renal corpuscle, both will be in the cortex, but one is outer cortex, one is inner cortex. Then the length of the loop of Henle. For the cortical one is short, and for the juxtamedullary is rather long. And there will be how far it goes into the outer zone or tip of the papilla. And there will be differences in blood supply of the tubule. These differences, they are about secondary capillary networks. Here you have peritubular capillaries, and here you have vasa recta. And the function of cortical nephrons will be formation of urine, and mainly the concentration of urine for the juxtamedullary nephrons. So the next question, which we are going to discuss, will be about the process of urine formation. As you can see on the slide, we have three steps of the urine formation. One is filtration, then goes reabsorption and secretion. So let's define each of these. Filtration, that's the process by which water and solutes from the blood leave the vascular system through the filtration barrier, which we have discussed, into the Bowman's space, and then follows into the tubular system. Reabsorption, that's the process of moving substances from the tubular lumen across the epithelial layer into the surrounding interstitium, and then into the blood vessels. Secretion, that's the process when you move the substances into the tubular lumen from the cytosol of epithelial cells back into the tubular system. And to recap, the kidneys, they are homeostatic organs, and this organ varies the excretion of water, electrolytes, and other hydrophilic molecules to maintain consistency of extracellular fluid composition. And urine formation begins with glomerular filtration of plasma at a rate of about 150 to 200 liters per day. And one of the questions which we will discuss in relation to filtration will be the glomerular filtration rate. So, a small summary on three major processes of urine formation. Please note the direction of forces. So, the filtration, this is when substances are filtered from the blood into the Bowman's capsule. Reabsorption, this is when substances are removed from the tubular system back into the blood. And secretion, this is when substances from the blood directly moving into the tubular system but bypassing the Bowman's capsule. And there might be a little bit of confusion between two such definitions as secretion versus excretion, because these two words, they look quite similar. So secretion, this is secreting the substances into the tubules from the blood or from the ECF into the tubular system, but these substances might not necessarily leave with the urine. Excretion is what leaves in the urine to outside. So this is what is excreted by the kidney. In other words, excretion means exit of the substance from the body, which means substances that are present in the body and those which will be present in final urine will be excreted from the body. And as you can see on the slide, amount of excreted substances in urine will be equal to amount that is filtered, how much is filtered, minus amount that will be reabsorbed because those substances they return back into the blood, and amount that is secreted will be added to the final excretion. So this is as for the secretion versus excretion. Now, few definitions which you need to know if you would like to understand functions of kidney. Glomerular filtration is the process by which substances they will enter the Bowman's capsule. And there is such parameter as glomerular filtration rate, which is briefly known as GFR. It is the amount of fluid moving into the Bowman's capsule per unit time. And here you can see the normal values for males or females. Or you can say that it will be ranging for about 180 liters per day. So glomerular filtration rate, it's a controlled variable, and in most circumstances, it is kept fairly constant. And few more things should be mentioned as for the glomerular filtration rate. The adequacy of the renal function is clinically defined. It could be clinically defined by the GFR. And kidney, like we have few general principles related to the GFR. And these principles are GFR is normally very large. As I said, it's approximately about 200 liters per day, which provides the potential to excrete multiple solutes that may be present at low concentrations in blood plasma. And the glomerular filter should not allow passage of blood cells or plasma proteins. And as we will discuss, the Starling forces are responsible for the net filtration pressure across the glomerular capillaries. And GFR is generally stable due to autoregulation, but it can be varied by active changes in afferent and efferent arteriolar tone, which we will also discuss, and I'll show you how it might change. So glomerular filtration fraction, that's another definition which you need to know, and it could be seen as the ratio of glomerular filtration rate to the renal plasma flow. And renal plasma flow, that's the amount of plasma flowing through the kidney per unit time. Usually it's taken per minute. And glomerular filtration fraction, that's the filtration rate as the percentage of total renal plasma flow that passes through both kidneys. So these are the parameters that will be usually determined in clinical practice to assess the functions of kidney. Now, let's discuss the filtration and mechanisms of it. How will it happen? The principle of filtration, it uses pressures to force fluids and solutes to move through the membrane, the filtration barrier. And it will be exactly the same in glomerular capillaries as in capillaries elsewhere in the body. That is known as Starling's law of the capillaries. And this is exactly what we have discussed in microcirculation for the cardiovascular system. What you need to remember is that high hydrostatic pressure at the glomerular capillaries, this is given in green, is due to the short and wide afferent arteriole, which provides low resistance to flow, and long and narrow efferent arteriole, which provides high resistance. And the balance of Starling's forces, it changes as blood passes along the glomerular capillaries from the afferent arteriole to the efferent arteriole. And hydrostatic capillary pressure, it is high along the whole capillary because the efferent arteriole is a resistant vessel. And other pressure which you need to consider, this is the oncotic pressure of the blood. And it increases along the glomerular capillary because fluid is being filtered, but proteins, they remain in the blood. Oncotic pressure of the glomerular capillaries, it might increase enough to prevent further filtration, at which point filtration equilibrium will be reached. So in the end, you have one force which will provide the filtration. That's the glomerular hydrostatic pressure of the glomerular capillaries. And because I said that no proteins are filtered, oncotic pressure of the Bowman's capsule, as you can see, will be equal to 0. So we are not considering this force under normal circumstances. And the addition of oncotic capillary pressure and hydrostatic Bowman's capsule pressure, it represents the sum of forces that oppose filtration, given in red. And when subtracted from the hydrostatic pressure of the glomerular capillary, this is the net filtration pressure, the final one, which is shown in the slide. So we have one force which favors filtration, and that's the hydrostatic pressure of the glomerular capillary. And you have two pressures which will oppose the filtration. That's the hydrostatic pressure of the Bowman's capsule and oncotic pressure of the capillaries. And here you have some values, and this is the resulting value of the net filtration pressure. And glomerular filtration rate could be seen as multiplication of filtration coefficient, which we will discuss in a while, and the difference of hydrostatic pressure minus two pressures which oppose the filtration. So at this stage, you should be able to name three functional layers of the glomerular filtration membrane that are shown in this slide. And also, you should be familiar with four principal forces governing the filtration flow across the filtration barrier. And you should be able to explain how these forces are related. So the next thing which we are going to discuss will be what are the factors that affect filtration, and what is filtered and what is not filtered. And finally, how much of a substance will be filtered. So what do we have? Factors affecting glomerular filtration. It will be changes of effective filtration pressure, those which are responsible for the net filtration pressure, and filtration coefficient. And also, what do we have in here? We have the filtration coefficient, which is the ultrafiltration coefficient as a product of permeability and surface area. So how permeable the filtration barrier is and which surface area do we have. So in the end, you can say that the glomerular filtration rate is the product of the net driving pressure forcing the fluid out of the glomerular capillaries, which is provided by the hydrostatic glomerular pressure, and opposing by the oncotic capillary pressure and hydrostatic Bowman's capsule pressure. And the permeability and surface area also affects the GFR. So other factors beside the pressures which might change the glomerular filtration rate will be the surface area, permeability coefficient, and also changes in renal blood flow. So let's take a closer look at the regulation of filtration pressure and how by changing the lumen of the afferent or efferent arteriole, you can change the glomerular capillary blood pressure. So as you can see on the slide, if there will be vasoconstriction of afferent arteriole, which basically decreases the blood flow into the glomerulus, there will be decrease in glomerulocapillary blood pressure, and as a result, net filtration pressure decreases, and there will be reduced GFR. The opposite, which is the dilation of the afferent arteriole, increases blood flow into the glomerulus. That will increase the glomerulocapillary pressure, and will increase the net filtration pressure. As a result, the glomerular filtration rate rises. Now, what about the efferent arteriole? If you will constrict the efferent arteriole, you will increase the arteriolar resistance downstream from the glomerulus. And in this case, it will lead to increase in hydrostatic pressure of the capillary and will increase the GFR. But if you will have simultaneous constriction of both afferent and efferent arterioles, these might have the counteracting effects on the hydrostatic pressure and renal blood flow. And the effect might be small increase, small decrease, or there might be no change. It depends on the degree of constriction. Now, afferent and efferent arteriolar resistance, constriction of either arteriole increases vascular resistance and reduces renal blood flow, while afferent arteriolar constriction decreases the blood flow into the glomerular capillary, thus decreasing the hydrostatic pressure and the GFR. And by the contrast, if there will be constriction of the efferent arteriole, which increases outflow resistance from the glomerular capillary, thus increasing the hydrostatic pressure in the glomerulus and increasing the GFR. And the filtration fraction that is seen as a proportion of renal plasma flow that is filtered, and that is normally about 20%, if constriction of arteriole reduces both renal blood flow and GFR, leaving the filtration fraction unchanged. While efferent arteriole constriction reduces renal blood flow but conserves the GFR, causing an increase in the filtration fraction. On this slide, you can see the summary of main factors that might affect the glomerular filtration rate. So what do we have here? The first one is the filtration coefficient. And here we need to talk about glomerular surface area, which might change because of the relaxation of glomerular mesangial cells. And this will result in increased GFR. The second one is the hydrostatic pressure of the capillary, which depends on renal arterial pressure or systemic arterial pressure. Then it also depends on afferent arteriolar resistance. In case of dilation, GFR increases because blood flowing through the glomerulus will be more. Then efferent arteriolar resistance. In case of efferent constriction, also GFR increases. Now, the Bowman's capsule hydrostatic pressure. Intratubular pressure might increase because of the obstruction of a tubule by the kidney stones or by extrarenal reasons present in the urinary system. And in this case, the GFR will decrease because the force which is opposing the filtration will be greater now. And the final one is the oncotic capillary pressure. Usually in relation to the oncotic pressure, we are looking at the cases where oncotic pressure decreases. This might happen due to the low concentration of plasma proteins, hypoproteinemia. And in case of reduced oncotic pressure, the force which is opposing filtration will become less, which makes the GFR significantly more. So let's once again take a look at the filtration barrier. What do we have here? And why we have to consider the structure. The functional significance of this anatomical arrangement is that it permits the filtration of large volumes of fluid from the capillaries into the Bowman space, but restricts the filtration of blood-formed elements and large plasma proteins, such as albumins. And what you have here is selectivity of the barrier is based on two main things, the molecular size and the electrical charge. And as for the size, you remember the fenestrated capillary and slits between the podocytes of the visceral layer of the glomerular capsule. So, as for the glomerular filtration barrier, substances with a molecular weight of about 10 kilodaltons are freely filtered. As molecular weight increases from 10 up to 70, there will be a roughly linear decline in the amount of solutes filtered. And albumins, which have the molecular weight of around 70 kilodaltons, is almost small enough to be filtered. But as you already know, albumins, they are essential and they don't have to be lost in urine. We have to preserve them because the plasma albumin concentration, that's the largest contributor to the plasma oncotic pressure. And the second thing which limits the filtration of macromolecules, it's the charge. There is less filtration of negatively charged macromolecules compared to neutral molecules of the same size, because they will be repelled by the fixed negative charges in the filtration membrane. As you know, same charges, they do repel. And at a physiological pH of extracellular fluid, that is 7.4, proteins carry net negative charges, which reduce their filtration. So it's not only the size, but also the charge. And once again, reminding you the 3 layers of glomerular filtration barrier. Here you have glomerular capillary endothelial cell layer. Here you have fenestrated types of capillaries, glomerular basement membrane, and the layer of podocytes. So, glomerular filtrate is modified by epithelial transport as it flows along the nephron. And what are the substances that are freely filtered? And does this mean that all of the substance will be filtered? So what does that mean if you say that substance is freely filtered? Substances that are present in the filtrate at the same concentration as found in plasma are said to be freely filtered. But please note that freely filtered does not mean all are filtered. The amount filtered is in exact proportion to the fraction of plasma volume that is filtered. So if it is known that the substance is freely filtered, it means the substance is filtered in a direct proportion to the concentration that you do have in plasma. So here on this slide, you can see the materials that are freely filtered. And here you have major electrolytes like sodium chloride, potassium, bicarbonates. Also you have metabolic waste products like urea, creatinine, metabolites. You also have glucose and amino acids, organic acids like ketone bodies, non-natural substances like inulin, para-aminohippuric acid, lower weight proteins, peptides like insulin and antidiuretic hormone, and myoglobin. So as you can see, actually a huge number of substances is freely filtered, but it's much more easier to remember which substances are not freely filtered. And here you have albumin and other plasma proteins and all the substances they carry, because you remember that the main function of plasma proteins is the transportation. And as you also know, lipid-soluble substances, they have to be transported by the plasma proteins attached to those proteins. What do we have among those substances? You have lipid-soluble bilirubin, thyroxine, and other lipid-soluble hormones, and also lipid-soluble vitamins like A, D, E, K. So the second step of the urine formation is the reabsorption. Kidneys, they reabsorb and redistribute up to 99% of the blood volume, and only 0.1% of the blood filtered becomes urine. So here you can see the summary of major substances and how much of the substance will be filtered and how much of that substance will be reabsorbed, which gives you the amount which is excreted. So for water, as you can see, and many solutes, up to 98 or 99 of the filtrate will be reabsorbed back into the blood. So here you can see like only 1 to 2 liters out of 200 approximately will be excreted per day. And variation of excretion rate in final urine usually reflects changes in renal tubular reabsorption. And the rate of reabsorption for most substances is highest in the proximal tubule. And fine control of the excretion usually occurs in the distal parts of the renal tubule, which we will discuss in a while, which receives a fairly constant fraction of the filtrate, which is about 10%. And the model of filtration reabsorption applies to most of the substances, as you can see on the slide. For others, such as potassium and hydrogen and some organic molecules, the rate of secretion also matters. Secretion into the urine across the nephron epithelia. And it might be the most important to consider as for the excretion. We will still discuss it in details, but as you can see, for example, glucose and proteins, they are filtered, but for the glucose, it will be completely reabsorbed and zero is excreted. And for the proteins, they are almost entirely reabsorbed and almost nothing is excreted. And also you can see the ratios of reabsorption for other substances as well. And please pay attention to creatinine, which is filtered but not being reabsorbed, because later on we will need it. So what about reabsorption routes? Here on the slide, you can see that there are two main options. We have transcellular reabsorption, and you also have paracellular reabsorption. Transcellular through the cell, like we have certain carriers, and paracellular in between the cells. So what are the possible types of transport of reabsorption? As you might remember, types of transport could be divided into active and passive based on whether the energy is consumed or not, and if it happens along concentration gradient or against concentration gradient. Passive types of transport includes diffusion, which could be simple and facilitated, and osmosis. And as you might remember, lipid-soluble substances, they can diffuse directly through the lipid bilayer and nothing else is needed. While water-soluble substances, they have to move through channels, and those channels, they could be gated, ungated. And if channels are gated, those gates could be opened and closed. And as for the active transport, it could be divided into primary and secondary, whether it uses energy directly from the ATP molecule or like secondary that is based on the primary one. Example of the primary active transport is sodium-potassium pump. And another classification of transport could be uniport, symport, and antiport. Symport when two substances are transported in one same direction. Antiport or counter-transport, you have two substances which are transported in different directions. And types of reabsorption also could be divided into obligatory and facultative. Obligatory reabsorption occurs when substance is obliged to be reabsorbed, and usually it happens in the proximal convoluted tubule. While facultative reabsorption, it occurs in collecting ducts and distal convoluted tubule, and it will be under the control of hormones, and secretion of those hormones depend on the concentration of a substance present in blood plasma. Now, another thing which we need to discuss is the renal threshold value. Renal threshold value, it's the level of a substance in its highest concentration in blood up to which it is totally reabsorbed from the glomerular filtrate. And all the substances, they could be divided into three categories. They could be high threshold substances, low threshold substances, and non-threshold substances. High threshold substances whose total amount may be reabsorbed actively, and examples of such substances include glucose, amino acids. They are excreted in urine only when their blood concentration is very high, which means when they exceed their threshold. Low threshold substances are reabsorbed only up to a small extent, like urea and uric acid. And we also have non-threshold substances that are not reabsorbed at all, like creatinine and para-aminohippuric acid. So why do we need to consider tubular reabsorption and threshold definition? As you know, for the glucose, we need a transporter protein, like it can be used for different molecules, ions, so that they can be reabsorbed. So on this slide, we are going to discuss such transporter for the glucose. And these transporters, they all have maximum transport that is shown in slide. And this is the capacity where transport carrier proteins, they get saturated. And for glucose, it will be of around 10 millimoles per liter. And if you over this value, you excrete the excess in urine. So this threshold can be a useful sign of disease, either due to the damage of kidney or other systems, like in case of diabetes mellitus. And beside the glucose as a high threshold substance, amino acids, they also have the transport maximum value. Because amino acids you are trying to preserve as much because they are useful nutrients for the body. So what about the renal filtration curves? What do we have in here? Renal titration curves could be used to determine the maximal rate of solute transport. This is, as I've mentioned, the transport maximum for solutes with saturable transport. Construction of titration curve requires calculation of the filtered solute load and urinary excretion rate. And for this, you have these two curves on the graph. For the range of plasma solute concentration. And net tubular transport is calculated from the difference of these two, which means the difference between filtered load and the excretion rate. So here you have to consider the plasma solute concentration at which the solute first appears in urine, that is called the renal threshold. And for the glucose, it will be around 200. And another thing which we need to revise is the type of cells in different parts of the nephron and collecting ducts. So here you have, as a reminder, a small summary of histology and types of epithelia present. Why you need to revise that? Because the structure of the epithelial cells, it will determine the function of that particular area and location. For example, in proximal convoluted tubule, you have a single layer of epithelial cells, which will have microvilli on their apical surface. And microvilli, they increase the surface area for reabsorption. As for the distal convoluted tubule, you will have two types of cells, like principal cells and intercalated cells. These are the sites for action for some hormones. And this is where, for example, secretion of potassium and hydrogen ions will occur. So we will discuss the reabsorption based on the areas of the tubular system, and we will begin from the proximal convoluted tubule. As you can see on the slide, what you have is reabsorption of about 65% of the filtered water, sodium, potassium, and 100% of most of the filtered organic solutes, such as glucose and amino acids. 50% of the filtered chloride, bicarbonates, almost all of it, and 50% of the filtered urea. And also, there will be a variable amount of the filtered calcium, magnesium, and phosphates in the proximal convoluted tubule. And also here, I would like to add that proximal convoluted tubule secretes variable amounts of hydrogen ions, ammonia, and urea. So this is the summary on reabsorption in proximal convoluted tubule. Now let's talk about sodium absorption. Sodium is absorbed by active transport mechanisms, and here it doesn't have transport maximum mechanism. What do we have? We have basolateral ATPases, which will help to establish a gradient across the tubular wall. So we have sodium-potassium pump, which pumps sodium out and potassium in. Proximal tubule is very permeable to sodium, so ions might flow down the gradient across the membrane, which is passive. And microvilli, as I have mentioned, they create a large surface area for absorption. Electrical gradient created also draws chloride across, so usually chloride follows the sodium. And as you know, sodium, it's osmotically active substance, so water will follow the sodium due to the osmotic force which is created. Means fluid left in the tubule will be concentrated. Now here you have an overview of segmental sodium handling along the nephron. So as you can see, the daily filtered load of sodium is far greater than the daily requirements for sodium excretion. And sodium balance is achieved with the filtration excretion of about 1 to 2%. And an overview of segmental sodium handling will be in proximal convoluted tubule, approximately 65% of the filtered sodium will be reabsorbed. The loop of Henle reabsorbs 20 to 25% of the filtered load, with about 10% of the filtered sodium consistently delivered to the distal tubule, and this does not depend on dietary salt intake. And final excretion of sodium will be determined by variable reabsorption along the distal convoluted tubule, which is called facultative reabsorption, that happens in distal DCT and collecting ducts. Now, the next important thing which we need to discuss is the glucose handling. Glucose absorption also relies upon the sodium gradient. So as I've mentioned, we have sodium-potassium pump or sodium-potassium ATPase, which pumps out the sodium, creating a low concentration of sodium inside the cell. And because of this gradient, sodium would like to enter. But the carrier protein is made in such a way that it's not only sodium, but glucose also should be attached to this carrier protein, like you can see given in the slide. This is the SGLT protein. And most of the glucose will be absorbed in the proximal convoluted tubule. At the apical membrane, we need sodium-glucose cotransporter, which you can see in the slide. And if plasma glucose concentration increases up to the value of about 180 to 20 milligrams per deciliter, glucose can be first detected in urine, because what will happen, there will be exceeded the transport maximum, means all of these carrier proteins that are present at the apical membrane will be fully saturated, so no more glucose can be reabsorbed. So the remaining glucose remains in the lumen and it will leave the body with the urine, will be excreted. And this is what is called the renal glucose threshold. So around 200 milligrams per deciliter, or it's about 10 millimoles per liter. Amino acid handling, the mechanism is pretty much the same as for the glucose. You also have to create the low sodium gradient inside the cell, which is provided by sodium-potassium ATPase. And you will also have a carrier protein, which has two sites, one for the sodium and one for the amino acid. And only in case of low sodium and a sufficient amount of carrier proteins, amino acids could be reabsorbed. If all the carrier proteins get saturated, then there will be increased protein loss with the urine. It can be also excreted in urine. Now, another electrolyte which has to be considered is the potassium. Potassium is the major cation in cells and its balance is essential for life. Even small changes, like as you can see from 4 to 5.5 millimoles per liter, which is known as hyperkalemia, can lead to fibrillation and death. What can happen if it's around 3.5 millimoles per liter? Cells will hyperpolarize, it will result in arrhythmias and death. Reabsorption of potassium happens in proximal convoluted tubule. And changes in excretion means potassium handling. It will be due to changes in secretion in distal convoluted tubule. And medullary trapping of potassium helps to maximize the potassium excretion when potassium intake is high. And potassium secretion, as you might remember, is provided by the hormone which is known as aldosterone. Now, potassium reabsorption along the proximal tubule is largely passive and follows the movement of sodium, and fluid in collecting tubules might also rely on active transport. And potassium secretion, which is important for potassium handling, occurs in cortical collecting tubule principal cells, those which we have mentioned, and relies upon active transport of potassium across basolateral membrane and passive exit across apical membrane into the tubular system. Now, the next step which we are going to discuss is reabsorption in the loop of Henle. As you can see here, there is a summary on the major components which will be reabsorbed in the loop of Henle. So it will be small amounts of water, electrolytes, chloride, bicarbonates, and variable amounts of calcium, magnesium, and phosphate. And loop of Henle sets the stage for independent regulation of both volume and osmolarity of body fluids, and this is what we are going to discuss in a while. But before that, you need to consider such definition as osmolality, the ability of solutes to lower the concentration of water, and it is a function of both the concentration of solutes and kind of solutes. For example, proteins are better than sugars, and sugars are better than small ions at lowering the concentration of water. So you can see here is the distribution of how each contributes. Osmolality is expressed in units of osmoles per kg of water, or more commonly milliosm per kg. Osmolality is often called osmotic pressure. And osmolarity and osmotic pressure have the same meaning, they are just expressed in different units. And osmotic pressure, which is created by the plasma proteins alone, without considering anything else, that is what is called colloid osmotic pressure, or more commonly known as oncotic pressure. So now we will talk about countercurrent multiplier. Countercurrent, it describes the flow of fluid down the descending limb and up the ascending limb, and critical characteristics of the loop which make them countercurrent multipliers. They are: the ascending limb of the loop of Henle actively co-transports sodium and chloride ions out of the tubular lumen into the interstitium, and ascending limb is impermeable for water, so here water could not be reabsorbed, while descending limb is freely permeable to water but relatively impermeable to sodium chloride. So water that moves out of the tubule into the interstitium is removed by the blood vessels that are called vasa recta. Thus, the gradient is maintained and water returns to the circulation. So let's take a closer look at the entire system. Fluid in the proximal tubule always remains isoosmotic with respect to plasma and makes no direct contribution to altering urine osmolarity. In the descending thin limb of the loop of Henle, osmolarity reflects that of surrounding medullary interstitium, and you can see at the beginning it is the same. And there is always some degree of hypertonicity in the medullary interstitium with a gradient of increasing osmolarity from the outer to inner medulla. So this is the gradient which ranges from 300 and reaches up to 1200 at the tip of the loop of Henle. And high antidiuretic hormone levels, they might dramatically increase the medullary osmolarity, which is passively reflected by increasing osmolarity along the descending thin limb. The ascending limb of the loop of Henle is called the diluting segment because sodium chloride is reabsorbed without water. So, as we mentioned before, descending limb is permeable for water and it might be reabsorbed, while ascending limb is not permeable for water but is permeable for sodium chloride, which could be reabsorbed. By the time that fluid leaves the loop of Henle, it is always hypotonic or dilute relative to plasma. Here you can see that's the value. And when antidiuretic hormone levels are low, the water permeability to the distal nephron and collecting ducts will be low. And hypotonic fluid entering the distal nephron remains hypotonic during passing through the collecting ducts so that the diluted urine is produced. And the maximal diluting capacity of the renal system is about 5 to 10 folds. But when antidiuretic levels are high, the water permeability of the distal convoluted tubule and collecting ducts will increase. So that will lead to the reabsorption of water. Osmotic water reabsorption from the collecting duct into the hypertonic medullary interstitium results in concentration of the urine. So small amounts of concentrated urine will be released. So as you can see, this medullary gradient, it is really very important for this kind of reabsorption in the loop of Henle. So how we can create that hypertonic medullary interstitium? The ability to concentrate urine depends on the generation of corticomedullary gradient, given in the slide, of increasing interstitial osmolarity. And formation of the corticomedullary gradient relies on the countercurrent arrangement of the descending and ascending limb of the loop of Henle and their different transport properties, which we have discussed now. The thin descending limb is characterized by high water permeability and lack of active transport. Osmolarity of the luminal fluid simply reflects that of surrounding interstitium. And the ascending limb has very low water permeability, and salt reabsorption into interstitium occurs in the ascending limb by active transport in thick ascending limb, and by diffusion in the salt permeable thick ascending limb, thin ascending limb. At any given horizontal level, the osmolarity of fluid in the descending limb and interstitium can be around 200 milliosmol per liter, greater than in ascending limb. And this is what is known as a single osmotic effect. And it is due to the salt reabsorption from the ascending limb. Amplification of the single effect in the corticomedullary axis. This is what we call countercurrent multiplication. And this is what is demonstrated in the slide. Another important thing which you need to consider is how to maintain a hypertonic osmolarity of the medullary interstitium. In most organs, interstitial fluid is similar to plasma, except of low protein concentration, due to the free diffusion between the capillary blood and interstitium. And in the kidney, the vasa recta capillaries, as you can see on the slide, allows trapping of solutes into the medullary interstitium. So, in the descending vasa recta, solutes diffuse into the plasma from the interstitium and water leaves by osmosis. Blood reaching the renal papilla is highly concentrated. And the ascending vasa recta solutes diffuse back out into the interstitium and water enters by osmosis. So the net effect of retaining high solute concentration in the medulla is known as countercurrent exchanger. So that's the second component of this system. The countercurrent exchange mechanism depends on low medullary blood flow. For example, in states of low antidiuretic hormone, medullary blood flow increases, causing washout of medullary hypertonicity that aids to the formation of diluted urine. So this is what is known as countercurrent exchanger and countercurrent multiplier. So here in the slide, you can see a small cartoon demonstration of how in descending limb the concentration changes because of the reabsorption of water, and in ascending limb reabsorption of sodium chloride into the interstitium, where the gradient is maintained fairly constant. And this is one more summary which shows you how formation of hyperosmotic urine happens in presence of antidiuretic hormone, which makes the distal convoluted tubule and collecting ducts permeable for water, which will be reabsorbed. And here you have three general processes that are required for the renal system so that we can vary the urine concentration. You need adequate glomerular filtration that is needed to deliver sodium chloride and water to the loop of Henle. Then, sodium reabsorption without water reabsorption in the ascending limb of the loop of Henle that dilutes the tubular fluid, providing the potential to excrete diluted urine. At the same time, the medullary interstitial fluid becomes hypertonic, as you can see on the slide, and provides the potential to concentrate urine in the collecting ducts. Water permeability, the third component, in the collecting ducts must be variable. And antidiuretic hormone, ADH, or also known as vasopressin, its plasma concentration is closely correlated with plasma osmolarity. And the normal set point for plasma osmolarity is around 285 to 288 milliosm per liter, which is associated with the low resting ADH concentration. Now, an overview of a countercurrent exchanger and multiplier. Multiplication happens in the Henle's loop and exchange happens in vasa recta, as we have discussed previously. And here you might have two outcomes: urinary concentration or urinary dilution, depending on the needs. And the basic requirements for forming concentrated urine are high levels of antidiuretic hormone because of the high osmolarity of the renal medullary interstitial fluid. And for dilution, the mechanisms for formation of diluted urine by continuous reabsorption of solutes from the DCT of the tubular system, while failing to reabsorb water, because in this case there will be no ADH provided. So maintaining plasma osmolarity within narrow normal limits, it depends on the ability to vary free water excretion in response to changes in water and solute intakes or loss. An increase in plasma osmolarity results in excretion of urine that is more concentrated than plasma. Some solute-free water is thereby returned to the extracellular fluid, and plasma osmolarity is reduced towards normal. Otherwise, a decrease in plasma osmolarity results in excretion of urine that is more diluted than plasma, and some solute-free water is excreted in urine, thereby increasing the body fluid osmolarity towards normal. And these changes in urine osmolarity can occur without significant changes in glomerular filtration rate or total solute excretion, whether the kidney produces concentrated or diluted urine. As you have seen, it depends on the antidiuretic hormone levels. And for the countercurrent mechanisms, one more component is important, which is the urea recycling, which also contributes to the maintenance of interstitial gradient in the renal medulla. And reabsorption in distal convoluted tubule and collecting ducts, as we said before, this is facultative. So the variable amounts of filtered substances, electrolytes mostly, could be reabsorbed in here. It depends on the concentration of hormones, which is determined by the concentration of a substance in blood. And as we also mentioned, distal convoluted tubule and collecting ducts, this is where you have principal cells for the reabsorption of sodium and secretion of potassium due to the action of aldosterone. And we also have intercalated cells which reabsorb potassium and bicarbonates and secrete hydrogen, which is important for the pH maintenance. And the final step, which is the tubular secretion, this is when transfer of materials from the blood happens into the tubular fluid. And the substances which are secreted, they include hydrogen ions, potassium, ammonium, creatinine, and certain drugs, for example, penicillin, like antibiotics. Tubular secretion has two important outcomes. The secretion of hydrogen, it helps to control the blood pH and thus contributes to the pH maintenance by kidneys. And secretion of other substances helps to eliminate them from the body. Here on this slide, you can see a summary on the reabsorption and secretion in different areas of the nephron. So here you have the summary on proximal convoluted tubule, then loop of Henle, then the distal convoluted tubule, and principal cells and intercalated cells with their functions, plus the renal corpuscle, which is responsible for the filtration. Now, finally, we are about to discuss methods of kidney examination. And here you have to know the composition of urine, which contains about 4% of solids, which include non-organic substances like water, electrolytes, protein-origin urea, that's the main product of protein breakdown, uric acid, ammonia, and other substances. Non-protein origin like salts and acids, and pigments like urobilin and urochrome. So here on the slide you can see characteristics of the normal urine. Volume, which varies considerably and depends on the water intake and environmental conditions. Color, usually it's straw yellow and depends on how concentrated the urine is. Then urine must be transparent with the specific odor. The pH ranges from 4.6 to 8, and it varies considerably with the diet. For example, high protein diet increases acidity, and vegetarian diet makes it more alkaline. And also another parameter which you need to know is specific gravity. And specific gravity also depends on the concentration of solutes, which depends on how much of urine is excreted. Here you can see some of the abnormal findings that might be found in urine, like albumins. If albumins will be present in urine, or proteins will be present in urine, this is what you call proteinuria. Glucose, when it's present in the urine, this is what is called glucoseuria. And now you already know that glucose appearance, that means that threshold of the urine, of the glucose reabsorption is exceeded, which means most probably in the blood plasma it's more than 10 millimoles per liter. Then, as you know, no formed elements must be filtered. And if red blood cells, they appear in urine, this is what we call hematuria. The other findings, they include ketone bodies, bilirubin, casts, microbes. So let's take a closer look at some of the findings. Proteins, or albumins. Despite high concentration in blood, albumin normally does not pass into the urine. Normally, protein excretion in urine is less than 150 milligrams per day, and the albumin fraction is about 20% of the total urinary protein and should be less than 30 milligrams per day or so. Some of the possible causes of proteinuria, they include abnormalities of the glomerular filtration barrier. So the most common reason is the damage of the glomerular filtration barrier, which will result into albuminuria. As we have mentioned, under normal conditions, it's not permeable. And also another case might be transient proteinuria. This might happen, for example, in case of heavy exercises. So how you can detect proteins in urine? You can use, for example, the urine dipstick test, or you can use 24-hour urine collection for protein and or albumin examination. Another pathological finding could be the red blood cells, which is called hematuria. Hematuria can be classified as gross hematuria, that is visible by the naked eye, and microscopic hematuria. This is visible only on microscopic examination of the urinary sediment. Microscopic hematuria is defined as the presence of 3 or more red blood cells per high power field in the urine sediment. And when approaching a patient with microscopic hematuria, you have to differentiate between the glomerular or extraglomerular reasons of hematuria. If red blood cells arise from the glomerulus tubular system, they might be trapped in a protein forming the red blood cell casts. And here you can see on the slide how these casts will look like. In contrast, the red blood cells that are of extraglomerular origin, they're smooth and biconcave. So basically they are the same as they appear in plasma. So what are the methods which are used to examine the kidney function? Here you can have urine analysis, blood tests like blood urea nitrogen, plasma creatinine, and renal plasma clearance. So clearance, if you will translate it, is reading the body of a substance. So the substance is removed from the body and excreted in urine, and it is defined as a volume of arterial plasma required to produce the amount of substance excreted in urine per unit of time. And units are volume per time. And clearance, it is critical to evaluate renal function. Here you can see the formula which is used to calculate the clearance. And clearance of substances with specific properties allows us to determine either glomerular filtration rate or renal blood flow. And this is what we're going to discuss now. Here you can see the picture showing how clearance principle works. And this is the formula which is used to calculate the clearance of a substance. So clearance of low molecular weight polysaccharide inulin is used to in experimental studies as an ideal marker for the glomerular filtration rate. And why it can be used to analyze the GFR is because inulin is freely filtered but is neither reabsorbed nor secreted by the nephron, and it cannot be metabolized. Therefore, the rate of inulin filtration equals the rate of inulin excretion in the urine, so the volume of plasma cleared per minute equals the GFR if you're going to use the inulin. While in clinical practice, serum creatinine, which is measured routinely by ordering a basic metabolic panel, is most commonly used to estimate the GFR. So you don't have to use the artificial substance, which is the inulin. And here you can see the normal ranges of creatinine for males and females. Creatinine is a product of a muscle metabolism, and it is suitable endogenous alternative to inulin. The rate of creatinine production in the body is fairly constant because it is a function of muscle mass. Creatinine clearance overestimate the glomerular filtration rate by about 10%, because in addition to free filtration, there is some secretion into the proximal tubule. So plasma creatinine is determined by the balance between the production rate and excretion rate. Because the creatinine production rate is constant and the excretion rate varies with the GFR, plasma creatinine is a direct index of glomerular filtration rate. So when glomerular filtration is low, creatinine is increased. Now, clearance also could be used to determine the renal blood flow. And for that, you might use the para-aminohippurate or para-aminohippuric acid. Using clearance to estimate the renal blood flow, the principle of clearance can be used to estimate the renal plasma flow rate using such marker as para-aminohippuric acid, which is the derivative of glycine. Para-aminohippuric acid clearance provide an estimate of the renal plasma flow rate because all of the para-aminohippuric acid entering the renal artery is excreted into the urine in a single pass through the kidney. Approximately 20% of the plasma para-aminohippuric acid is filtered. At low plasma concentrations, the remaining 80% entering the peritubular capillaries is secreted into the proximal tubule by organic anion transporters. And the term effective renal plasma flow rate is sometimes used to describe para-aminohippuric clearance, since the measurement relates to plasma flowing to functional nephron units. So this is the clearance of para-aminohippuric acid, which is used to count the renal blood flow. So a small summary: creatinine is normally, which is normally present in the blood and is not reabsorbed and minimally secreted by the kidney, is used in clinical practice to determine the GFR. Para-aminohippuric acid clearance, which is equal to renal plasma flow because this substance is removed from the blood and by the kidney through the combination of filtration and secretion, and thus it can be used to know the renal plasma flow. Thank you for your attention.